Hey folks, welcome to this episode on calculating heat. So just recall some of the definitions that we saw in our last lesson. Thermal energy is the sum of all the kinetic energies of all the particles of the system, and this cannot be measured. It can, however, be transferred in the form of heat. Temperature, on the other hand, which is denoted by T, is a measure of the average kinetic energy of these particles of the system, and it can be measured. So remember that kinetic energy, thermal energy, is related to our temperature. It's directly related. And so when we look at the temperature before and after a change, either physical, chemical, nuclear, this can provide us with an idea of the amount of heat that entered and left the system. This is the key. Okay, so if we look at before and after a change, this allows us to figure out the amount of heat that entered or left the actual system. And this is the concept that we're going to be using to calculate what we are eventually going to call enthalpy. So heat Q, it's the transfer of the thermal energy between two objects. Now it's not just a straight, it could be not just be a straight transfer. There's a lot of different factors involved. One of them, in terms of heat, the factor involved is mass. The other thing is something that we call the specific heat capacity. And finally, the temperature change. So we're going to be looking at these three different things together and see how they influence how much heat is transferred from one object to another. Now overall, when we look at this equation, Q is equal to mc delta T. So again, m is mass in grams. Okay, so if we had something in kilograms, we'd change it into grams. Specific heat capacity is joules per gram degree Celsius. Now this is generally how we measure specific heat capacity. Sometimes you might see kilojoules in there, but mostly it's joules per gram degree Celsius. And finally, our change in temperature is measured in degrees Celsius. So again, the three things that affect our heat is temperature change, mass, and the type of substance. So the first factor that we're going to look at is temperature. And again, temperature is directly related to our heat transfer. Based on the second law of thermodynamics, it states that heat is always transferred from the object at a higher temperature to an object to the lower temperature until both objects are at the same temperature. So when we look at these two situations here, we have an object that is hot and it's transferring thermal energy in the form of heat or as heat to something that is cool. In the second situation, we have something that is very hot, transferring thermal energy to something that is cold, or obviously very cool, cold. The difference in temperature between this and this versus this and this is a lot less in this case than it is over here. And so remember that in the second law of thermodynamics, it transfers thermal energy until both objects are at the same temperature. Meaning that if we wanted to take something that is very hot and very cold and bring it to a midpoint that has the same temperature, there's going to be a lot more heat being transferred from this thing than there is over here. So what we can say is that the temperature change between this and this versus this one is going to be a lot bigger. So that temperature change of this is going to be a lot bigger than the temperature change we see over here. Now remember the system and the surroundings. If we had a flask and we had a system in here, these particles that are reacting, and let's say, for example, the temperature change of the water, so again, we're measuring the water here, and the water in this case is what we call the surroundings. If the temperature change is positive, if we have a change in temperature that is positive, aka, how do we get a temperature change? Well, the T initial was 10 degrees Celsius, and the T final was 20 degrees Celsius. So if we took 20 minus 10, we would get 10 degrees Celsius. And remember that that sign would be positive. So if the temperature change was positive, what that means is that for the water to have increased in temperature, it must have gained thermal energy. Where did it gain thermal energy from? Well, it gained thermal energy from the system. Now, going back a few lessons, we also have to remember that law of conservation of energy, that energy is not created or destroyed, only transferred. So whatever amount of energy that is lost from the system is gained by the surroundings, and we can see that as temperature. So if the temperature change was positive, remember that our Q is equal to mc delta T, assuming that mc stay constant. If we had a positive temperature change, that means that we had a positive heat change. Okay, so that means that the thing that we're measuring, in this case the water has gained heat. Okay, and that's what we see. Our operators tell us the direction of flow of our heat. And again, it's important to understand what we're measuring. We are measuring the temperature of the water, we're not measuring the temperature of the system. And because the temperature of the water has increased, we can say that that water has gained heat. And the only way that water could have gained heat, if we did this in an isolated system, for example, the only way that it could gain heat is through the loss of heat in our actual system. Now, another factor that affects the amount of heat is the mass of these objects. So again, going back to temperature, temperature is looking at the average amount of kinetic energy in, for example, samples. Here we have two beakers. Again, they're at the same temperature, meaning that they have the same average kinetic energy. However, one of these required more energy to get to that 25 degrees Celsius. Could you guess which one? This one over here. If you ever tried to boil, if you had a kettle and you had a small amount of water versus a kettle that had a large amount of water, which one required more time, aka more energy in this case, just a very simple relationship, which one required more time and energy to actually heat up to 100 degrees Celsius or 90, whatever the kettle does? It's going to be this one over here because there's more energy required to bring all of the particles to have the same average kinetic energy as it would for this one over here. So the more particles, it means that more heat must be transferred to increase the kinetic energy of these particles in that substance. So again, to bring this one to 25 degrees Celsius and this one to 25 degrees Celsius from maybe 0 degrees Celsius, this one will require more thermal energy. Remember that thermal energy is transferred, and it's transferred in the form of heat. So more thermal energy transferred to this means that we'd have to have more heat transferred. And finally, we look at specific heat capacity. Now in the slide, there are a few different definitions that we use for different situations. The first one is a very basic definition. It's called the heat capacity, and it's the amount of heat required to raise the temperature of a substance of any mass by 1 degree Celsius. And again, so you can see there are very, very slight differences in these definitions. The specific heat capacity, which we're going to use for our Q is equal to mc delta T, the specific heat capacity is what we're going to be using for that. And it's the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. So here we have any mass, and here we have 1 gram. Another one that you might see is molar heat capacity. Again, it's the amount of heat per mole required to raise the temperature of 1 mole, which is 6.02 times 10 to the 23 of substance, by 1 degree Celsius. So the unit of measure changes in these definitions, and this is the one that we're going to be using the most in our calculations. So when we look at, for example, here we have this glass of water in this pool, the question is which one of these will have a higher capacity, and a higher heat capacity, and which one of these will have a higher specific heat capacity. So just take a moment and think about it. So looking at the first question, says which one will have a higher heat capacity. The answer to that one is the pool. Now think about it. If we had this glass over here and we had this pool with massive amount of water, which one of these would take more energy to raise the amount of the temperature of all this water by 1 degree Celsius? It would be the pool. Okay? The pool has a lot more water than this one over here, and therefore would require a lot more thermal energy than this glass over here, and therefore it has a higher heat capacity. The second question says which one will have a higher specific heat capacity. The answer is they're both the same, because they're both water, assuming that the water is the same, chlorinated and fluorinated the same way. But this water and this water will actually have the same specific heat capacity because it is the same substance. So on that note, the substances that we deal with have a very specific heat capacity associated with them. Now again, these can change depending on impurities within the actual substances, but as a general note, these are the accepted values. Now these are all determined experimentally by looking at how much heat is required to actually increase the temperature of 1 gram of this by 1 degree Celsius, but you can see that we get these various numbers over here. Now the unit for specific heat capacity is joules per gram degree Celsius. Again, the amount of energy, joules, required to increase the temperature of 1 gram, G, by 1 degrees Celsius. So when we look at these different values over here, let's say for example we compare aluminum with something like water. Okay. Which one of these would require more energy to increase the temperature of 1 gram of substance by 1 degree Celsius? Well, in this case, the bigger the value, the more energy is required, because this is going to be connected. So this will be read as 4.18 joules per gram degrees Celsius, meaning that 4.18 joules of energy is required to increase the temperature of 1 gram of liquid water by 1 degree Celsius, whereas aluminum only needs 0.900 joules for every gram degree Celsius. As we mentioned before, the sign conventions tell us the direction that heat is traveling. So if we had our system here and we had our surroundings, okay, again including this Erlenmeyer flask and everything else, the universe basically, if we look at the sign convention, we can tell where heat is going. Now, one thing to note is that in this case, we are measuring heat of our system. Okay, so in this case, our Q of our system is going to be positive. Now, what that means is that our system is gaining heat. Now, the only way that system can gain heat, if we again look at law of conservation of energy, is by loss of heat from the atmosphere. Okay, so the atmosphere has to lose heat in order, or lose thermal energy in order for the system to gain thermal energy, meaning that heat travels into the system. Now, what that means, because the system is gaining thermal energy and it's increasing its heat, we call that endothermic. Okay, so endothermic means that the system is taking in thermal energy. On the opposite side, when we look at Q of our system is going to be negative, in that terms negative heat, that means that the system is losing energy. What that means, if we looked at the Q of the surroundings, the Q of the surroundings would be positive. Okay? Because again, if the Q of the system, if the system loses heat, then the surroundings must gain it. So because the system is losing heat, it's losing thermal energy, and the energy is being transferred to the surroundings in the universe, we call that exothermic. Exo meaning exit, and thermal energy. So it's losing thermal energy. So these sign conventions will be of very, very good value to us when we look at our actual calculations. So let's do an example over here. Our first example, it says how much heat must be absorbed by the water in a kettle to raise the temperature of 1.25 kilograms of said water from 16.4 degrees to 98.9 degrees Celsius. So the first things first is it's looking at heat. So we're trying to calculate Q. Now there's a few things given to us. Now we have this kettle. It has a certain amount of water. Now this is going to be a physical change, not a chemical change, because it's going to, maybe it actually won't even be a physical change. It might not actually boil. It won't pass the boiling point of water, but we are going to be bringing the temperature of our water up a little bit, meaning that it probably will absorb some heat or some thermal energy from the atmosphere. And the atmosphere in this case would be the power cord. So the mass of the water in this case is going to be 1.25 kilograms. And the specific heat is not given to us, but we know that it is talking about liquid water. So from our chart beforehand, what we know is that this is going to be 4.184 joules per gram degrees Celsius. Our T initial is going to be 16.4 degrees Celsius, and our T final is going to be 98.9 degrees Celsius. So to figure out the heat, we use our formula. Q is equal to mc delta T. So in this case, mass has to be in grams. So that means that we have 1250 grams multiplied by 4.184 joules per gram degrees Celsius. And then multiply that by our final, our final temperature, which is 98.9 degrees Celsius minus 16.4. So if we do this all out, what we should get is and again, when we look at significant figures, we have 3, 4, 3, 3, so our answer should be in 3 significant figures. Our answer is going to be 432 kilojoules. Okay. Now you can see that I kind of skipped a step here. We would get an answer in joules, but it's a lot more acceptable to write big numbers in kilojoules rather than scientific notation. So we would take the 432,000 joules divided by 1,000 and get our kilojoules. Now one more thing here, I'm just going to make it very obvious that we get 432 kilojoules. What that means is that the water, again, that's the thing that we're measuring, the thing that we're measuring the temperature of, the water is gaining 432 kilojoules, okay, of heat. Okay, so attempt this one by yourself. It says how many grams of aluminum can be heated from 90.0 degrees Celsius to 120.0 degrees Celsius if 2092 joules are applied. The specific heat of aluminum is 0.900 joules per gram degree Celsius. Now, one thing to note is that in the beginnings, we will be giving you these values here, but remember that specific heat is always going to be found in our tables. So whenever it's not given to you and you think you should need it, always look at your data tables to find out that specific value. Okay, so pause the video and try to attempt this question now. All right, pause, we'll come back with the answer. Okay, so I've listed out the unknowns here and the knowns. And again, everything is in the right units. we have degrees Celsius, we have joules per gram degree Celsius. And one thing to note is that this is very important, that these two values have to match, that the joules have to match, the grams have to match, and degrees Celsius have to also match. So we start off with our heat equation. Q is equal to mc delta T. And we are solving for mass, which means that we have to divide by C delta T by both sides. And that gives us M is equal to Q over C delta T. So our joules, we put our joules on the top, we put a specific heat, which is already given to us. We look at our temperature change, and we get something with three significant figures, 3, 4, 3, and 4. So lowest is 3. So we get 77.5 grams of aluminum. All right, try this one next. It says a 15.75 gram piece of iron absorbs 1,086.75 joules of heat, and this causes its temperature to change from 25 to 175 degrees Celsius. Calculate the specific heat capacity of this iron. So once again, pause the video, attempt it, we'll come back with the answers. So once again, what we have is, again, we've listed our knowns and unknowns. And we start off with our Q is equal to mc delta T. Now in this case, we're looking for a specific heat capacity of iron. Now this could be very simple. You could look at your data table, but it's asking you to calculate it, so we'll go through the steps here. So our C, because we want to solve for a C, we've divided both sides by m delta T. And here are our joules. Again, we have to make sure that our joules, we have to get the unit into joules because our specific heat capacity, the unit is joules per gram degrees Celsius. So we need to have our units in joules, grams, and degrees Celsius. So we have our joules there, we have our grams there, and we have our temperature change over there. And what you'll notice is that we get joules divided by grams degrees Celsius, which is, again, the same unit that we expected over there. And so we get 4.6 times 10 to the negative 1 because we have two significant figures over here, and that is our answer for this question there. And finally, our last practice question says, what was the initial temperature if 250 calories were applied to 100 grams of gold, and the final temperature of gold was 175 degrees Celsius? The specific heat capacity of gold is 0.129 joules per gram degree Celsius. Now, one thing to note is this value over here is very, very small, which gold can change its temperature very, very easily with a very small amount of heat applied. One thing that you'll have to remember is that our specific heat is in joules. This value of heat is in calories, so we're going to have to change this value into joules somehow. And also, we're going to have to separate our temperatures because we're looking for our initial temperature, and we are already given its final temperature. So go ahead, attempt this question, press pause, and we'll come back with the answers. Okay, so here we start off with our calories in this case, and we want to get to joules. So remember, 1 calorie is equal to 4.184 joules. Multiply that, we get our joules. We already have our grams, specific heat, and our final temperature. We need to look for our initial temperature. So once again, we start off with our Q is equal to mc delta T. But what we're going to do is we're going to expand this delta T into T final minus T initial. Now what you can see is that this term over here, this operation, is being multiplied by mc, and we want to get this isolated as best as we can. So we want to divide both sides by mc, and what we get is we get T final minus T initial is equal to Q over mc. However, when we put in our value of 175, we can see that, again, we need to isolate for our Ti. If we bring this to the opposite side over here, we'll get minus 175, but we're left with a negative value for Ti. So what we're going to have to do is we're going to have to multiply this entire term by negative 1, giving us a Ti of positive. After that, we just simply put in our values, and again, we have, here we have 4, 4, 3, 3. So our final answer should be 3 significant figures. In this case, our initial temperature is 93.9 degrees Celsius, meaning that our gold has absorbed some thermal energy. It has absorbed heat because it started off at a lower temperature than its final temperature, and that makes sense because the amount of energy that it absorbed was in the positive. So it had a positive value, meaning it absorbed heat, and that would make the temperature actually rise. So thanks very much for watching this episode. See you next time.